So welcome to this second part of dissociation extraction. Let us just start by revising quickly what we have done in the first part. So we have started looking at dissociation extraction. In the previous class, we have looked at concepts of acids and bases, what we mean by an acid. So we call it as a Bronsted acid if it tends to lose a proton, or if it tends to accept a lone pair, we call it as a Lewis acid. And correspondingly, we also call the bases as Bronsted base or a Lewis base. We talked about how do we write the equilibrium, the Ka value for this equilibrium, the dissociation of the acid, the equilibrium for the dissociation of acid. And because the equilibrium constant has a very wide range, 10 raised to minus something to 10 raised to plus something, we tend to write it in the same way as we do for pH. So we write it in terms of pKa, that is minus log to the base 10 Ka. So if I know the pKa value for a particular acid or a base, we can calculate the value of the equilibrium constant Ka as 10 raised to minus. So this means Ka would be 10 raised to minus pKa. Okay, and of course we need to take into account the ionic product of water. So for a particular compound, pKa plus pKb would be equal to 14. So we talked about this last time. Lower pKa would mean that it would be higher acidity. We talked about this last time, right? And we talked about basic solutes as well. Higher pKa would mean higher basicity. Higher pKa would mean lower pKb, and therefore lower pKb would mean more basic compound. Okay, so we talked about this. Just refresh from your previous lecture. Then we talked about the relationship between the pKa and the degree of dissociation at different pH values, right? So we remember this problem. We talked about if I say that benzoic acid has a pKa of 4.2, then at pH 4.2 it would be 50% dissociated somewhere here. If phenol has a pKa of 10, that means at pH 10 it would be 50% dissociated. And then depending on the pH value, we can calculate the degree of dissociation. This is basic physical chemistry kind of calculations. I want you to recollect all of that. If not, just revise your previous undergraduate stuff so that you are better prepared to understand this concept of dissociation extraction. Then we did a couple of problems. In this problem, the point to be noted is that we are writing overall distribution coefficient as a ratio of the compound in the organic phase to the compound in the aqueous phase in all forms, whereas the distribution coefficient D is just the ratio of the undissociated compound in the organic phase and the aqueous phase. So recall that D prime is different from D, and then the relative separation factor is something that we will talk about today. And then we did one more problem of paracresol getting dissociated and extracted into the aqueous phase from an organic phase, and we talked about how this dissociation equilibrium helps to extract more of this paracresol in the aqueous phase. So we did part A. Part A was the dissociation plus extraction, and part B was without the dissociation. And you can see from your answers in your previous problem of A and B that how the dissociation extraction, how the dissociation and then neutralization of the paracresol by using NaOH in the aqueous phase actually helps to get more of paracresol in the aqueous phase. So recall this previous lecture, if not revise the lecture. Okay, what we are going to do is now extend this to two compounds. So for example, if we have a mixture of weak acids in the organic phase, okay, let's say we have 2,6-xylenol, let's call it as A. So this is our A, and let's call this paracresol as B. So HB, we are going to denote it as HB because there is a dissociation that is happening, and we are going to call 2,6-xylenol as HA. So these are the pKa values. So 2,6-xylenol pKa is 10.62 and paracresol pKa is 10.28. So if you want to write the Ka value for 2,6-xylenol would be 2.399, almost 2.4 into 10 raised to minus 11, and for paracresol it will be 5.248 into 10 raised to minus 11. So you can see the dissociation equilibrium constant for paracresol is higher, right? That means it would get dissociated to a larger extent, and therefore it has more acidity. So paracresol is more acidic. So let's say paracresol is more acidic than 2,6-xylenol. Okay, recall. Now what I want you to think first of all is which is the stronger acid. Okay, we talked about that. So paracresol is the stronger acid. Now imagine that what we are doing is in the organic phase, right? In the organic phase, so this is our organic phase and this is our aqueous phase. In the organic phase we have HA and HB. So you see HB is paracresol. Now this is HB is more acidic. Now aqueous phase, what we are going to do is we are going to take a base like NaOH, and this base we are going to take stoichiometrically deficient. So it is a limiting reagent. So that means the base is a limiting reagent. Or a limiting reactant, which we can say. And because it is a limiting reactant, it would preferentially react with more acidic compound, paracresol in this case. So the dissociation, subsequent neutralization of paracresol into the aqueous phase is going to be more than that of 2,6-xylenol. 2,6-xylenol will also get dissociated, also get extracted, get dissociated, get reacted with NaOH, but because it is lesser acidic, having lower acidity, more of paracresol is going to come now in the aqueous phase, right? So it is going to react now preferentially with paracresol. So we can say that B minus ions, the paracresol getting dissociated, neutralized, will have more concentration in the aqueous phase. So B minus in the aqueous phase is going to be much more than A minus in the aqueous phase. Now if you say dA and dB, that means now dA, remember what dA is? The distribution coefficient for A in the organic phase with respect to aqueous phase, concentration in the organic phase divided by concentration in the aqueous phase. So if dA is more than dB, then what is going to remain more in the organic phase? Just think and tell. Yes, 2,6-xylenol would remain more in the organic phase. So you see now how we have been able to take the benefit of more acidity of paracresol so that it gets more extracted into the aqueous phase, which has the NaOH, which has the base, whereas paracresol being whereas 2,6-xylenol being less acidic and having higher distribution coefficient remains preferentially in the organic phase, right? So just think, if you want, just rewind this lecture and see for yourself. So this way we have been able to keep more of 2,6-xylenol in the organic phase and get more of paracresol in the aqueous phase, right? You see, so once this more paracresol comes in the aqueous phase, now we can separate the aqueous phase. So separate the aqueous phase. Obviously separation is not going to be complete. I'm not going to have all the 2,6-xylenol in the organic phase and all the paracresol in the aqueous phase. That's not going to happen because there is only a small difference in the acidity. You see, they are both are of the order of 10 raised to minus 11. This Kb dissociation constant for paracresol is about 2.5 times, but it's not very large. Okay. So if you separate the aqueous phase, so the aqueous phase will now have more of B minus ions and less of A minus ions. Now how do I regenerate paracresol? So I take this, and if I add acid like H2SO4 or HCl, then this dissociated paracresol ions that are there in the aqueous phase, they will give me back the HB, and then HB can be separated from the aqueous solution. So aqueous solution had Na plus ions and B minus ions and A minus ions. Now if I add H2SO4, the aqueous phase now will have HB in the undissociated form, that means as a paracresol, and I will have sodium sulfate if I have added H2SO4, or sodium chloride if I have added HCl. Right, obviously HCl is much more, sodium chloride is much more corrosive, the chloride ions are much more corrosive, so we prefer to add H2SO4, easy, cheap also. So and then we can now separate the HB, the paracresol, from this aqueous solution which contains the sodium salts of these compounds. Okay, so that's how we have been able to separate. Obviously there will be some amount of HA as well, whichever is coming from these A minus ions, but you can see that because HB is more acidic, more of it has come in the aqueous phase. HA has a more distribution coefficient, so it has remained preferentially in the organic phase. So that's how in one theoretical stage, so this you can think of as one theoretical stage, we have been able to get some separation of the paracresol from 2,6-xylenol. Okay. So just make sure that you understand this conceptually, and if you have understood this conceptually, then you can go forward. Till that time you revise and you think, and once you go forward, what we will do next is we will start looking at all these things in a more quantitative manner. So we will try to quantify exactly how much paracresol comes in the aqueous phase, how much 2,6-xylenol remains in the organic phase. All those things we'll quantify, and then we'll play around with all these parameters and see how these things are affected by different parameters, like how much, what is the strength of the NaOH, and so on. Okay, so make sure that you understood this part. If you understood, then only go forward. Okay, so let's start doing this quantitatively. Here is a problem that we can take. So let's say 2,6-xylenol paracresol. Suppose the distribution coefficient for 2,6-xylenol is 36. Distribution coefficient for paracresol is 12. So you see the distribution coefficient of 2,6-xylenol is 3 times. That means that's how much 2,6-xylenol likes the organic phase as compared to paracresol. Let's say the total concentration, initial concentration, so we can think about this in two parts. The total initial concentration, so this is the initial part. The total concentration of both the acids in the organic phase is 1 molar, and ratio of the initial concentrations is 1. So that means HA in the organic phase initially is 0.5 molar. HB initially in the organic phase is also 0.0 molar. So delta is 1 as well as the total is 1 molar. Let's say the initial normality of the base, the NaOH that we are taking, is 1 molar. So that means the aqueous phase NaOH concentration is 1 molar initially. Remember, all this is initially. Now let's what do we want? We want a stoichiometrically deficient base, isn't it? So suppose I take the organic phase as 1 liter. That means we would have 0.5 plus 0.5, we would have a total 1 mole of the organic acids, xylenol as well as paracresols. Both put together would be 1 mole. So now if I want it stoichiometrically deficient, suppose if I take 1 liter, that means I will have base also, total base also would be 1 mole. Okay. So that means they would be stoichiometrically in exact stoichiometry, 1 mole of the acid in the organic phase and 1 mole of the base in the aqueous phase, right? So we are going to take now stoichiometrically deficient. So let's say if I take the aqueous phase as 0.5 liters, that means now the total moles of NaOH would be only 0.5 moles. So you see 0.5 moles are stoichiometrically deficient as compared to the 1 mole of the total acids in the organic phase. Okay, so that's how we are taking the base to be deficient. Base is deficient, stoichiometrically deficient, stoichiometrically limiting reactant. So now allow equilibrium to happen, allow equilibrium to take place. We take it in a let's say a separating funnel. We shake that separating funnel for let's say half an hour, 1 hour. So allow equilibrium to take place. So once the equilibrium attains, what we are going to have is HA is going to be in the organic phase, HB going to be in the organic phase. Some of the undissociated HA is going to be in the aqueous phase, undissociated HB is going to be in the aqueous phase, and in the aqueous phase HA is going to dissociate. So we are going to get A minus ions, we are going to get B minus ions, and arising out of the dissociation, we are going to have H plus ions in the aqueous phase. Both these are going to dissociate, both of them are going to contribute to H plus ions, but the H plus ions are there, and in the aqueous phase we also have Na plus ions, we also have OH minus ions, right? So you see, let me just write all the ions here. So we have Na plus ions as well, and we have OH minus ions as well. I have just written all the negative ions on one side and all the positive ions on the other side, cations and anions. Okay, because we also have to think about, so think about the electrical neutrality, all those things will come. So we have to think about all these dissociation equilibria. We also have to think about the ionic product of water, because H plus multiplied by OH minus ion concentration, H plus ion concentration multiplied by OH minus ion concentration is going to be at the most 10 raised to, is going to be equal to 10 raised to minus 14, the ionic product of water. So that constant also comes into picture. Okay, so what I want you to do is find concentrations of all the species in the organic and aqueous phase at equilibrium, and hence find the separation factor. So this is what I want you to do. Try this on your own. Try this problem. Okay, I want you to do it on your own. Let it take 2-3 hours, doesn't matter, but you try it on your own. Only once you have done it yourself, then only go forward. Okay, pause the video, try it now, don't go forward. Okay. Okay, now if you have tried, here is the solution, or I'm not going to tell you the solution, I'm going to tell you the solution methodology, procedure, if you like. Okay. Okay, so we have said that we have OH minus ions here, we have H plus ions here. Okay, we don't know any of these concentrations, so let's assume that HA undissociated in the aqueous phase we denote by some variable, let's say X. HB in the aqueous phase undissociated we denote by a variable Y. If you take these two as unknowns, X and Y, now we can say HA in the organic phase is going to be 36 times X. Why? Because DA is 36. HB in the organic phase is going to be 12Y. Why? Because DB is 12. I told you this as a problem statement. DA is 36 and DB is 12. Okay. Now, so I have got the concentrations of A and B, HA and HB in the organic phase in terms of X and Y. Now all I have to do is relate these concentrations of ions, in terms of X and Y, and once we do that, we would be able to get equations and solve for X and Y. That's what we are going to do. So try this yourself. Pause, take this as a hint, pause and do it yourself. Pause and do it yourself. Okay. Okay, here is the answer. Here is the answer. Oops, here is the answer. Here's the answer. Okay, so what have we said? We said that H plus into A minus divided by HA in the aqueous phase, everything in the aqueous phase, the dissociation is happening in the aqueous phase. This is equal to Ka. And what was the Ka? Ka was pKa was 10.62, and therefore Ka was here. Ka was 2.4 into 10 raised to minus 11. Let's just round it off. 2.4 into 10 raised to minus 11. Okay. H plus into B minus divided by HB, everything in the aqueous phase, is equal to Kb. What is Kb? Kb was here 5.248. Let's just round it off to 5.25 into 10 raised to minus 11. So 5.25 into 10 raised to minus 11. Now HA in the aqueous phase is nothing but X, isn't it? HB in the aqueous phase is nothing but Y, right? So I don't want this H plus concentration to be there, because I don't want to solve for H plus. H plus we can find, but we don't need to solve for that. We want A minus ion concentration and B minus ion concentration in terms of X and Y. So one of the ways we can eliminate that is to take the ratio of these two, right? So we take the ratio of these two. So if you take the ratio, you will have A minus divided by X, and you will have B minus divided by Y, and that Y will go in the numerator. This would be equal to, the 10 raised to minus 11 would cancel. It would be 2.4 divided by 5.25. Let us just calculate that. 2.4 divided by 5.25. Let's calculate. 2.4 divided by 5.25. This is 0.457. We had already calculated that right here. 0.457. So I can write A minus divided by B minus concentrations in the aqueous phase would be 0.457 X divided by Y. This is our one equation that relates A and B. All right. Now, what else can we say? Right. Second, the electrical neutrality. Remember, this aqueous phase has to be electrically neutral. That means the total moles of positive ions, or total concentration of positive ions, and total concentration of negative ions must cancel each other out. That means I must have Na plus concentration plus H plus concentration must be equal to OH minus concentration plus A minus concentration plus B minus concentration. All the concentrations of positive ions must be exactly equal to all the concentrations of sum of all the concentrations of negative ions. Electrical neutrality. So electrical neutrality. There must be no net charge in the aqueous phase. Now, one more simplification we can do is this H plus ion concentration is going to be very small as compared to Na plus ion concentration. Remember, Na plus ion concentration is 1 molar. We have taken Na plus ion as 1 molar, NaOH as 1 molar. So Na plus ion concentration, NaOH is completely dissociated, is going to be 1 molar. So this H plus ion concentration is going to be small as compared to Na plus ion concentration. Similarly, because H plus ion concentration is small, OH minus ion concentration is also going to be small. A minus and B minus, we are having them as 0.5 molar. Right? So even if some of it comes, the concentrations of A minus and B minus is likely to be significantly high. They are going to be high as compared to OH minus ion concentration. So I am going to neglect the OH minus ion concentration as compared to A minus ion concentration and B minus ion concentration. Okay. So if that is the case, then I have another equation between A minus ion concentration and B minus ion concentration, that A minus plus B minus is going to be equal to Na plus, which is equal to 1 molar. We have taken 1 molar. 1 molar. Okay. So this gives me another equation for X and Y. Second equation for A minus and B minus ions. So look at these equations 1 and 2. I can solve them together and I can get a concentration of A minus in terms of X and Y, B minus ion concentration in terms of X and Y. Let's just do that. So equation 1 will give us A minus would be equal to, or we can write it as B minus if you want. B minus would be A minus ion concentration into Y divided by 0.457x divided by 0.457x. B minus ion concentration would be A minus ion concentration into Y divided by 0.457. Now if I substitute, this is our equation 1 rewritten in a different form. Okay. And our equation 2 is here. So I can now simplify equation 1. See, A minus ion concentration plus B minus. Now I will write in terms of A minus, so A minus into Y divided by 0.457x would be equal to 1, and then I can take A minus ion concentration common, so this would become 1 plus Y divided by 0.457x is equal to 1. So I'm going to have A minus ion concentration, let me write that here, would be 1 divided by 1 plus Y divided by 0.457x, right? Just simplify it, multiply throughout by 0.457x, numerator as well as denominator, and this would become 0.457x plus Y. Make sure that you are getting up to this. Make sure that you have got up to this so far. Make sure that you have got up to this so far. Okay. Now B minus ion concentration, what would that be? B minus concentration would be A minus concentration into Y by 0.457x. So if I simplify, this would be Y divided by 0.457x plus Y. So you see, now I have A minus ion concentration also in terms of x. I have B minus ion concentration also in terms of x, right? So I have this in terms of x, I have this in terms of y, this is in terms of x, this is in terms of y. A minus now I have in terms of x and y, B minus I have now x and in terms of x and y. The OH minus ion concentration is going to be negligible as compared to A minus and B minus, and H plus is going to be negligible as compared to Na plus concentration, and this is going to be 1 molar. Okay, so now I have two unknowns, x and y. Okay, now we can use the overall material balance for HA and HB and solve for x and y. Pause and do this for yourself. Pause and do this for yourself. Okay. Let me rub this out now. Let me rub this out. I don't need them here. I'm sure you've done it yourself. Only then go forward. Only then go forward. Okay, what did we have initially? What did we have initially? This was 1 liter, this was 0.5 liter, this was 1 molar, this was 0.5 molar, this was 0.5 molar. Now look at the material balance for HA. Look at the material balance for HA. Write a material balance for HA. Right? So material balance, let me write that properly here. Material balance for HA. How much HA did we have initially? 1 liter into 0.5 molar. That was what was initially. And after equilibrium, we must have the same moles of A minus. Either it could be A as HA or it could be as A minus. So either it is HA in the aqueous, HA in the organic, and A minus in the aqueous. Right? Do you realize that? So at equilibrium, this is initially. At equilibrium, I must have the same amount. Right? So it would be 1 liter of organic multiplied by 36x, that is the concentration, so many moles, plus 0.5 liters of aqueous multiplied by x, that is the concentration of HA, plus 0.5 liters into the concentration of A minus. A minus ion concentration is 0.457x divided by 0.457x plus y. Same way, material balance for HB. Initially I had 1 liter of organic into 0.5 molar, so that was 0.5 moles. At equilibrium I will have 1 multiplied by 12y coming from the organic phase plus 0.5 multiplied by y coming from the undissociated Hb in the aqueous phase plus 0.5 multiplied by concentration of B minus ions, that is y divided by 0.457x plus y. So these are our two equations for x and y. So solve them and then we will get x and y. Once you get x and y, you can get everything, because everything else we have written in terms of x and y. Right? Pause and do this for yourself. Pause and do this for yourself. Don't go forward until you have solved it yourself. Right. I'm sure you have done it yourself. Here is the final answer. Our x would be 0.00982 m. So this is 0.00982 molar. This y is 0.01134 molar. A minus ion would be 0.284 molar. B minus would be 0.716 molar. You see, now A minus and B minus ion concentration are in molar. Therefore, OH minus ion concentration is going to be very, very small as compared to these. Right? Because the base is stoichiometrically deficient. I have not generated those many OH minus ions. So our condition for getting, for this condition, A minus ion concentration plus B minus ion concentration equal to 1, normality equal to 1 is correct. Because we have taken base stoichiometrically deficient. If we had taken base in excess, then we would have to worry about OH minus ion concentration, and therefore we would have to invoke the ionic product of water. Okay, now so we would get HA in the organic phase also, HB in the organic phase also. Now you see the separation factor alpha AB. So what is the separation factor? This is your separation factor is in terms of distribution, overall distribution coefficient for A as compared to overall distribution coefficient for B. Okay. Not dA by dB but dA prime by dB. Now what is dA prime? HA in the organic divided by HA in the aqueous plus A minus in the aqueous divided by HB in the organic divided by HB in the aqueous plus B minus in the aqueous. Numerator is HA in the organic, denominator here is the denominator of the first part, dA prime, is HA existing in the aqueous phase as undissociated plus the dissociated, the total HA, total HA exists as undissociated as well as dissociated as A minus. Okay. And dB prime, the denominator for dB prime is HB, total HB in the aqueous phase, the dissociated form as B minus ions as well as the undissociated form HB. Okay. So see that you get this answer for yourself. Now if you have done it already, I would like you to make an Excel sheet out of all this. Do these calculations in Excel. Put all these things as variable. The initial concentration, the pK, the initial T, the initial delta. Put all these as variables. Okay. Because now we are going to see different things. We are going to see this problem with different parameters. Okay. First thing that we are going to do is repeat this problem for different case. Let's say total moles of the base is 0.5 moles and change. So now change the normality of NaOH and the V organic by V aqueous ratio. So the total moles of the base remain as 0.5 moles, but change normality and the V organic by V aqueous ratio. So what we had taken was one normal and we had taken 0.5 liters of the aqueous. So V organic by V aqueous was 2. So remember, V aqueous we had taken as 0.5 liters. This is what we had taken. Okay. So V organic by V aqueous was 2. Now take this, change the normality. Okay. Change the normality. Suppose I take 2 normal, 4 normal. I want only 0.5 moles. So then V aqueous, I will have to take 0.25 liters. Or for this particular case, I will have to take V aqueous as 0.125 liters. So for this particular case, the V organic by V aqueous phase ratio would be 4. In this particular case, V organic by V aqueous, the phase ratio would be 8. Or take the normality to be 0.5 molar, 0.5 normal. Okay. Then the V aqueous would be 1 liter. And then the V organic by V aqueous would be 1. Phase ratio would be 1. So do the whole problem again for these cases. Okay, pause, do it for yourself, then only see the answer. Here's the answer. Okay. Change normality from 0.01, 0.1, 0.5, 1 to 5. Okay. Change it over a very wide range. If you have done an Excel sheet, changing and getting answers would be very, very straightforward. Okay. Next thing I want you to do is change the normality, make it limiting or excess base. Okay. What I want you to do is take the same ratio, phase ratio, V organic by V aqueous, but change the normality 0.1, 0.2, 0.71. So when it is here, when it is 0.5, so when it is here, now that means the base is stoichiometrically equal to the not here. This is the case that we have done. This is the base case that we have done. This is the case that we have done. So when you go to here, then we will have base equal stoichiometrically to the HA and HB that is there in the organic phase. Okay. So but be careful. Once you go to this case, once you go to the excess base case, then the assumption that H plus is going to be far less than Na plus, and this breaks down. Well, this may be still valid, but the other assumption A minus plus B minus is going to be far greater than OH minus. This assumption breaks down because now the base starts to become excess. So then you have to invoke ionic product of water. That H plus ion concentration multiplied by OH minus ion concentration would be equal to 10 raised to minus 14. Okay. Another case. So you see how alpha AB, the separation factor, changes. Okay. Next case. I wanted to take the normality same, but change the mole ratio. Change the not mole ratio, change the phase ratio. So V organic by V aqueous 10. That means aqueous phase is 0.1 liter. Aqueous phase is, this ratio is 5, that means aqueous phase is 0.2 liters. Then this is 0.5 liters. This is the case that we had done. Okay. And the other cases also. Again, you will see that as you go towards this case, you will have to invoke ionic product of water, because then the base is becoming molar equivalent to the acid that is present. Pause this video, do these calculations for yourself. Make sure that you have understood everything and you are able to do all these calculations yourself. Okay, let's go forward. Just like we have done the dissociation extraction of weak acids, now we can think about doing dissociation extraction of weak bases. So if you imagine, when you make pyridine, you also get the 3 picoline and 4 picoline. So this is 1, 2, 3 picoline and 4 picoline as a side product. Now you need to separate them. So one of the ways to separate them, they have very close boiling point, they have very good solubility in water, they have almost the same log KOW, but their basicity differs. Their basicity differs because the alkyl group is para position or alkyl group is meta position. And you look recall from your organic chemistry lecture how the organic the methyl group being present in the meta or the para position makes the base weaker or stronger. You see that pKa is 5.66, 6.03. So tell me which is more basic. Remember, pKa plus pKb is equal to 14. So higher the pKa means lower the pKb. So that means 4-picoline is a stronger base as compared to 3-picoline. So if they are dissolved in the organic phase, now we will take an aqueous phase which will allow the base, more of the base, stronger base to come into the aqueous phase, right? And then we have to neutralize that. So the aqueous phase now we will take would be acidic. We will add an acid like H2SO4 or HCl. We'll do calculation with HCl first. Okay. So remember now, write all these equilibria. I want you to write these equilibria for yourself. In the aqueous phase, the A that has that has come into the aqueous phase is going to get protonated, is going to react with H plus HCl, and I'm going to have AH plus and I'm going to have BH plus in the aqueous phase, and they will react with H plus depending on their reactivity, depending on their basicity. You see, 4-picoline was more basic. So more of BH plus is going to form, more of B is going to come into the aqueous phase, and more of A is going to remain in the organic phase. Right? Write the equilibria for yourself. Pause and write it yourself. Okay, this is the equilibria that we are going to write. Either this or you can write it like this. Okay. And then take the ratio, or take the ratio of these two reactions, it will be the same. It will be like this. Okay. Go forward. These are the equilibrium constants we are going to write. Now if I want to eliminate OH minus ion from here, I will take the ratio. So Ke would be Ka divided by Kb. Okay. You know the pKa values. Okay. So calculate the pKb. pKb would be 14 minus 5.66. So this would be 14 minus 5.66. 14 minus 5.66. This would be 8.34. And this would be 14 minus 6.03. This would be 14 minus 6.03, 7.97. So this Ka, the dissociation, or now in this particular case it's not dissociate, it's not, the base is not getting dissociated, the base is getting protonated. So the Ka that we have for this protonation reaction here, Ka we have is 10 raised to minus pKb, and this Kb would pKb for A, and this would Kb would be 10 raised to minus pKb for B. So Ka would be, so Ka would be 10 raised to minus pKb for A. What is pKb for A? pKb for A is 8.34. 10 raised to minus 8.34, and Kb would be 10 raised to minus 7.97. Okay, so do this problem. Okay, and overall distribution coefficient, this is how we are going to define, and separation factor, this is how we are going to define dA prime by dB prime. Okay. Okay, so we have done this, we have answered this. Stronger base is 4-picoline. You see, Kb, the protonation constant is higher, more of it will be protonated. That means it is more basic. So stronger base is 4 picoline. So if I add acid which is stoichiometrically deficient, it would react preferentially with 4 picoline, and therefore BH plus is going to be more as compared to AH plus. And if DA is going to be higher than DB, then 3 picoline would remain preferentially, A would remain preferentially in the organic phase, and that's how we have done the separation. So now imagine we have done the separation. We have organic phase, we have aqueous phase. Now this aqueous phase has the protonated base, protonated 3 picoline or protonated 4 picoline. So we had A and we had B. So this became A and B in the aqueous phase. In the aqueous phase, it got protonated as AH plus and BH plus. Let me write this bigger. Let me write this bigger. So we had organic phase, we had aqueous phase. Organic phase has A, organic phase has B. It gets equilibrated, the pure distribution of A and B. Now it gets protonated as AH plus and it gets protonated as BH plus using HCl if you want in the aqueous phase. So now BH plus is going to be more in the aqueous phase and A is going to remain more in the organic phase. So now if you separate, now you will have aqueous phase. Now if you neutralize that aqueous phase, we will have AH plus and we will have BH plus and we have H plus and we have Cl minus. Okay. Now if you add, of course there is A also and B also, undissociated A and B also, that is also there in the aqueous phase. So now if you add NaOH to neutralize this HCl, this will go back to AH will go back to A and BH plus will go back to B. That's how we will get more of B. So now after neutralization, I will have more of B in aqueous phase and more of A in the organic phase. That's how we have been able to do the separation. That's how we have been able to do the separation. Okay. So think about that. Let's do a problem. But in this particular case, I want you to do all this in terms of variables. So what I want you to do is, let's say the total concentration of the base in the initial, of course, initial concentration of the base in the organic phase is T as A and B organic, and initial concentrations in the organic phase ratios is delta A organic divided by B organic, and we add N as the initial mole of HCl. Okay. I want you to derive an expression like you had done for the first case. You have done actual calculations with values. I want you to do the calculations in terms of delta, in terms of T, in terms of N, in terms of dA and in terms of dB. Okay. Do this for yourself. Pause, do this for yourself, then only check whether you got the answer. Okay, let me just show you what I want you to do. Okay. What I want you to do is, organic phase is here, aqueous phase is here. I will have A in the organic phase, I will have B in the organic phase, I will have A in the aqueous phase, I will have B in the aqueous phase, I will have AH plus in the aqueous phase, I will have BH plus in the aqueous phase. I want you to say that this is equal to X, this is equal to Y. Okay. So this A at equilibrium, of course, now we are writing, this would be dA multiplied by X. This B would be dB multiplied by Y. Okay. If I write the equilibrium like we had done last time, and if I use the electrical neutrality, I want you to write this in terms of X and Y. I want you to write this in terms of X and Y. Of course, dA will be there, dB will, T will be there, delta will be there, all those things will be there. Now I want you to write the material balance for A, what we had initially, just the same way as we had done the reactive dissociation extraction of the organic acids, paracresol and 2,6-xylenol. Look at that and do the same way. Only thing is we have done it, we want to do it in terms of the variables T, delta, N and dA and dB. So you'll have all these 5 variables. So all these concentrations you will have once you solve for X and Y using material balance. All these concentrations would be in terms of dA, dB, Ka, Kb, T, delta and N. Okay. Do this. Here's the answer. You will find that alpha AB is this expression. Derive it yourself, then you will see for yourself. Now, reason for doing it in the variable form is we can do certain manipulations and see for ourselves what can happen. So first manipulation we are going to see is that T tends to 0. T tends to 0 means what? That this tends to 0. Or another way of saying it is the N is far in excess of T. That means the acid that we have added is far in excess. So either say T tends to 0 or N tends to infinity. Another way of saying this is N is far greater than T. If N is far greater than T, then this second term is negligible. And then this numerator and denominator will cancel out. And then alpha AB would be dA by dB, Kb by Ka. That is the maximum possible separation factor. Maximum possible. Now you can take the previous problem and see for yourself that alpha AB, what is the maximum separation factor? dA was 36, dB was 12 for 2,6-xylenol and paracresol. And Kb by Ka, Kb by Ka, Kb by Ka. Where did that go? Kb by Ka. Ka by Kb is 0.457. Ka by Kb is 0.457. Right? Ka by Kb was 0.457, 0.457. You see, this is the maximum separation factor we can get. Okay. Look at another way. If T tends to infinity or N tends to 0, which means T is far greater than N. That means as if there is very little acid here, which means it's like physical distribution. Then as if there is no effect of the dissociation equilibria. So then alpha AB would be, just if you do this, simplified from here. Okay, pause and do it for yourself. Pause and do it for yourself. Simplify from here. T is infinity, N tends to 0. That means then this term will cancel out. This T will cancel out. Now simplify. You will find that alpha AB is equal to dA by dB. So in the 2,6-xylenol paracresol case, the minimum possible alpha AB was 36 by 12, 3. No dissociation. There is no effect of dissociation extraction. There is no effect of neutralization using the base. Right? Same way here. Okay. Now do this for yourself. And for this particular case, if you take these cases, if you take these concentrations, where those go? If you take these concentrations, you will have, for this particular case, so Ka is this, Kb is this. For partitioning from chloroform solvent, 17.31 and 16.38. What is the maximum alpha AB, minimum alpha AB, and alpha AB if T is equal to 1, delta is equal to 1, and N is equal to 1. Do this. Either you can substitute directly here, or you can actually solve using these values, just the way we had done earlier, X and Y. Okay. So you'll find that maximum alpha AB is 2.48, minimum alpha AB is 1.06 and actual alpha AB is 2.35. Just one small extension is obviously I am not going to have complete separation of A and B. So we need to do this multiple number of times. Okay. So it has to be a counter current kind of extraction. That is one point. Second point is, let's not add NaOH or so let's go back to this previous case, the 2,6-xylenol paracresol case. So suppose I add a base. So I have, in this particular case now, I have the, what do I have? I have the Na salt of A and NaB salt of B in the aqueous phase, right? Suppose I take base such that one of the salts, let's say this salt, precipitates out. So we are having dissociation, we are having extraction, and we are having precipitation of the sodium salt of B. Right? Say sodium salt sodium salts are usually soluble in aqueous, but suppose I take a base such that the salt of B minus is insoluble in the aqueous phase. Now that's going to drive this equilibrium even more forward. That's going to drive this equilibrium even more forward. So then almost all the B is going to come in the aqueous phase as the precipitated salt of B, and essentially all the A is going to remain in the organic phase, right? So let me just give you an example for that. An example from literature. 2,6-xylenol and paracresol. So rather than taking NaOH, if I take piperazine as a base, it's an organic base, and the salt is insoluble, then you see separation factor jumps to 500s. Okay. Complete separation even in one theoretical stage. Or let's say our case 3-picoline, 4-picoline. If you take para-toluene sulfonic acid as a extractant in the aqueous phase, an organic acid rather than HCl, then the para-toluene sulfonated 3-picoline or 4-picoline would be insoluble. It will precipitate out, and then the separation factor would become very, very large, 120s. That is reported in the literature. You can do this experiment yourself and find it for yourself. So you see, so now we are talking about dissociation, extraction, and precipitation or crystallization, if you like, to enhance the separation factor. So that's what I wanted to cover in this part of dissociation extraction. Revise and get all your concepts properly in place, and then you can we'll go on to the next part of the syllabus.